Let's talk about an invisible force that's all around us all the time. It's a force that governs our world from the deepest oceans to the highest skies. It's how a massive steel ship can float, how a car stops with just a light touch of your foot, and yeah, how a giant airplane gets off the ground. That force is pressure. And once you understand it, you unlock the secrets to some of engineering's greatest marvels.
Which brings us to this mind-bending question. I mean, seriously, how does a jumbo jet weighing hundreds of tons lift itself into the sky using nothing but air? It seems impossible, right? Well, it's not magic, it's physics. And by the end of this, you'll know exactly how it works.
Now, you'd think to understand flight in the thin air miles above us, we'd start in the sky. But nope, our journey actually begins deep underwater, because it's down there where you can practically feel the weight of the water, that the basic rules of pressure become crystal clear.
So what is liquid pressure? Well, just imagine it as the weight of all the water in a column directly above a certain point. But here's the wild part. That force isn't just pushing down. At any single point, that pressure is pushing out equally in all directions. Up, down, sideways, you name it.
Now, what's really fascinating is what doesn't affect the pressure. You'd think a huge lake would have more pressure at the bottom than, say, a skinny little tube of water, right? Wrong. It only comes down to two things: depth and density. Go deeper, the pressure builds. Use a denser liquid like mercury, and the pressure goes through the roof. The shape of the container, totally irrelevant.
And if you want a perfect real-world example of this, just look at a dam. Because the pressure gets so much stronger the deeper you go, the force pushing against the bottom of the dam is just immense. That's why engineers have to build them way, way thicker at the base just to hold all that water back.
Okay, so we have established that water has weight and it exerts pressure. But that kind of creates a puzzle. A tiny little steel bolt will sink to the bottom instantly. So how in the world can a massive ship made of thousands of tons of that exact same steel just float on the surface?
The answer comes from an absolute legend from ancient Greece, Archimedes. His big idea was actually pretty simple. When you put an object into a fluid, that fluid pushes back. We call this upward push the buoyant force, and its strength is exactly equal to the weight of the fluid that the object moved out of the way.
So it's really a tug of war between two forces, the object's weight pulling it down and the buoyant force pushing it up. If the object's weight wins, it sinks. But if the buoyant force can perfectly match the object's weight, you get a stalemate. It floats. The genius of a ship is its shape. That huge, hollow hull displaces a massive amount of water, creating a buoyant force that's strong enough to perfectly balance its own incredible weight.
All right, so we've conquered floating. Now let's move on to something that feels like a straight-up physics magic trick: multiplying force. How do you turn a small, weak push into an incredibly powerful shove? Well, it's all about our next principle of pressure.
I mean, think about this for a second. How can your foot, with just a gentle push on a pedal, bring a 2-ton car to a screeching halt? You don't have super strength, but your car's hydraulic system, it kind of does.
The secret is something called Pascal's principle, and what it says is that for any fluid in a sealed system, like the brake lines in your car, if you apply pressure at one point, that pressure is transmitted instantly and equally to every other point in that fluid, no loss of power. And this is exactly how your brakes work. Your foot pushes a small piston, which creates pressure in the brake fluid. That pressure zips through the brake lines to much bigger pistons at the wheels. And since pressure is force spread over an area, that same pressure acting on a larger area creates a way bigger output force. It clamps the brake pads down and stops the car dead in its tracks.
This is the whole point of hydraulics. They are incredible force multipliers. A small, easy push from you can be amplified 10, 20, even 100 times on the other end. This is the powerhouse behind everything from a simple car jack to those giant construction excavators.
So we've mastered pressure in liquids, we've multiplied force. Now, let's take that knowledge up into the air. It's finally time to answer that big question we started with. What is the secret of flight? All right, the key to flying is Bernoulli's principle. And honestly, this one can bend your brain a little, so stay with me. For any fluid, and that includes air, it all boils down to this: the faster it moves, the lower its pressure becomes. I'll say that again. Fast-moving fluid means low pressure. Slow-moving fluid means high pressure.
And an airplane wing, or an aerofoil, is basically a masterpiece of engineering designed to exploit that fact. See how the top surface is curved and the bottom is flatter? That shape forces the air flowing over the top to travel a longer distance, which means it has to move faster than the air underneath. So what do you get? Faster air on top creates a zone of low pressure. The slower air below creates a zone of high pressure, and that pressure difference results in a powerful upward force. That, my friends, is lift.
And if you want the absolute best proof that this works, just flip the wing upside down. What do you get? A race car spoiler. Here, the goal is the complete opposite of lift. By making the air underneath move faster, you create high pressure on top and low pressure on the bottom. The result is a powerful downforce that literally glues the car to the track for better grip. It's the exact same principle, just inverted. Now, a lot of people make the mistake of thinking the low pressure above the wing sucks the plane up, and that's not quite right. A much more accurate way to think about it is that the high pressure zone below the wing is actively pushing the plane up toward that area of lower pressure. So lift isn't a pull from above, it's a powerful push from below. So we have floating ships, we have hydraulic brakes, and we have airplanes that fly. 3 totally different applications, but they are all connected by one constant overarching force that affects everything in our world. And that force is atmospheric pressure. It's easy to forget, but we are all living at the bottom of an invisible ocean of air. And all of that air, miles and miles of it, has weight, and it's pressing down on everything, all the time, with incredible force. This is the stage on which all these other principles play out. So, to wrap it all up with the big ideas, you have Archimedes' principle, where buoyant force lets ships float. You have Pascal's principle, where pressure is transmitted equally, letting hydraulic brakes multiply force. And you have Bernoulli's principle, where faster fluid means lower pressure, giving us the lift that makes airplanes fly. So from the crushing force at the bottom of the ocean to the subtle pressure difference over an airplane's wing at 30,000 feet, these fundamental laws of physics are always there, always working, and they are incredibly powerful. And that kind of leaves us with a final thought. These amazing principles were discovered centuries ago by some brilliant people who were just paying attention. It really makes you wonder, what powerful, invisible force of nature might we be overlooking today, just waiting for someone to notice? Thanks for joining me.